Okay. So we were discussing conditional expectation. Okay. So we defined, if we have two random variables, of course, defined on the same probability space, then we defined P y given x. Shall I recall the definition or you remember it? If you remember those who didn't come to the class yesterday, they also remember it? Okay. 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 I don't have to recall. Okay. No worry. Okay. So anyone want to recall? No. You want to recall? Okay. So you should tell me, no? Otherwise, will I know whether maybe you saw the video or maybe you understood it's not clear. So the point is this: you have two random variables, x and y. Okay. Then the density function x given, this is the density function defined x given y, which we write it like this. This is just probability of x equal to x, okay, given, sorry, y equal to y. This is not to get confused, let me by y by x, okay. Probability of y equal to y given x equal to x, that's all. Right now, this is the density function. This is the conditional density function given y x equal to x, y and x, okay. Conditional function, which is a function of y given x. X is fixed here, okay. Then this is a function of x, right? This is a chi yx at x is equal to this as a no. The function of this is expectation with respect to this. Expectation with respect to this is summation y, this function f y given x of y x. Okay. Now you take the expectation. This gives the density function. This is the density function, which is defined as a conditional density function. You take the expectation of f with respect to this density function of y, which is summation y this. So this is y. Y, I mean, it's only countable sum, but I write it as y in R. Okay? It's only, I mean, otherwise it's zero, except that countable number of points. Okay? So it is this. Now, if you have any function, this chi is a function from R to R. Okay? X is a function from omega to R. Okay? Now you can compose these two functions. And E of y given x is just this chi of x. What was correct initially? What is x? Here x. This is fine. This is fine. This is a function of x. Conditional expectation with respect to x is a function of x. I will make it more clear by the end of this class. Okay. Now, given any random variable y and x, we get a function of x as the conditional expectation. Let us see example. Okay. So suppose if you have x and y are independent and Poisson independent, and x follows Poisson lambda, okay, and y follows Poisson with respect to mu, lambda mu greater than 0. Okay. Now we want to compute this. We want to compute what? We want to compute expectation of x given x plus 1. Of course, x and y are independent, so x given y is just x. Or we want to compute this. Okay. To compute this, first we have to compute this. I mean, we want to compute this. Okay. X and x plus y are dependent, of course. Okay. If x given y is, I mean, if they are independent, x and y are independent, you can see that it will sum it up, and I mean, you will see that E of x, y given x when x and y are independent is E of, I mean, y itself. Okay. E of y given x is equal to y itself. Okay. You can follow, I mean, you can look at it and then you will know that. Yeah. No, sorry. It is E of, sorry, E of y. It is E of y, sorry. It should be a function of x, no? It is E of y. If you do the computation, it's clear. It's E of y. Okay, this is clear? E of y is a number. Sorry, E of x.
The expectation of chi of x is expectation.
No, no, E of y given x, what is that? That is just, let me, okay. When x and y are independent, what is y given x? E of y given x. Hmm?
No, but here is not a notation, right?
No. Let's just compute it. Now let's just see what is there. F of y given x of x, y, x. Okay. It is going to be f of xy by fx, right? Right. Which is, wait a minute, f of fx times fy times fx, which is just fy. Okay, we get fy. So if you just compute that summation y fy, which is just expectation of y. Okay, expectation of y is a function. Yeah.
It is a result that thing is a random variable.
Yes.
Which gives the value e of y everywhere.
That's what I'm saying. So it is just e of y. This is equal to e of y.
Yeah. Gives the value.
Constant random variable. It's a constant variable. Okay. A constant random variable. Yeah, it's a random variable. I'm not saying it's not y. Y is not a function of x. So it's e y given x. If you do the, here is the computation. You want to compute the f y x, this is equal to the joint density divided by fx. Joint density is the product. Okay, so fx get cancelled and you get only fy. Summation y, here you will get only fy. Summation y fy is just the expectation, and it is equal to that. Okay? I mean, even I don't remember, but we can do the computation and find it. Of course, it is a random variable. Expectation of y given x is a random variable. It is in fact a function of x. Okay, but here the function is constant function. Okay, that's all. So now we have a situation where x and y are independent, but we want to compute that x given x plus y. What is that? Okay. So to compute that, we first have to compute this, right? Okay, x and z. Okay, right? This is what we want to compute first. X bar x plus y. Here x is z, some number. Okay, x is z. So this is, of course, so this is just f of x comma x plus y of x z, okay, divided by f of x plus y of z. Okay, right? If you want n k, you can write. I mean, these are integer x z. They are all integer. I'm just writing x z. Okay, but they are integers. Okay. Okay. Now, if x follows lambda, Poisson lambda, y follows Poisson mu, we have proved that x plus y, when they are independent, follows lambda plus mu, Poisson lambda plus mu. We have proved that using moment generating motion, or directly we computed it also by computing the convolution. Okay. So this implies we can directly write it, what it means. This is just going to be, first one is x, x. So, I mean, this is just going to be, basically, this is equal to, this one is equal to f xy with x z minus x, right? Same thing. You just write the definition. This is equal to probability of x equal to x and x plus y equal to z, which is same as probability of x equal to x and y equal to z minus z. Okay, this is so this is just the product of these two things. Huh? X plus y has become this. You write the definition of this z minus x. Okay, so x plus y z, and this is equal to fx at x, fy at z minus x divided by fx plus y at z. Okay, now this whole thing, I'm writing it here. I mean, sorry, I came like this. Okay, this is equal to, you just write the definition, which is just x power, lambda power x by x factorial e power minus lambda, correct? This is the probability of this, right? Then that is mu power z minus x by z minus x factorial. Okay, then e power minus mu, minus mu, saying mu, but I'm writing that. Okay, this is okay. Then bottom one, maybe I should have written it somewhere. I'll write it again. I'll write it here. So that is equal to, let me write it again. First one is lambda power x x factorial, x is integer, sorry, e power minus lambda, and this correct, no? Yeah, mu power z minus x e power minus mu by z minus x factorial. Then the whole thing divided by, I mean, let me write it big bar. I will just, okay. So the whole thing divided by lambda plus mu, that is. So lambda plus mu power z. Z is x plus z. Okay, just z. Z divided by z factorial. Okay, times e power lambda plus. Okay, so we can cancel these things. Okay, now what do we get? We have lambda here. So this is just lambda by lambda plus mu power x, mu by lambda plus mu power z minus x. Okay, I've just grouped it together. Then it is just the NCR, it should be, which will be z factorial will go to the top. So z, that's all, no? There is x factorial z minus, that is okay. X z. X factorial z minus, I mean, unfortunately, I have decided to write, instead of k and n, I have decided to write x and z, which is confusing even to me. No, I just said for integers, I have denoted with x and z, which is confusing for me. Okay, but this is right what I have written. This is just binomial, right? Okay, so this is just the binomial distribution. I mean, the point is, when you have x is Poisson and y is Poisson, then this f given x plus y at x z follows binomial. This is the binomial. What is that? Binomial density with p equal to lambda by lambda plus 1. Okay, with n, with this and n. What is n? N is z. Okay. Okay. But the thing is, we want to compute the conditional expectation. That will be different. What is the conditional expectation? We have to take the, so now we have, this is a function of z, right? We have to take, this is a function of z. Function of z or x? No, this is a function, no. We have to submit, take the expectation with respect to x, then we will get a function of z. Okay, whatever that chi I said, chi of x given, let me write it and then explain it, of this at z equal to summation of x of whole thing, whatever I call it as p or something. Like it's okay, I will just write it, x into lambda by lambda plus mu power x and mu by lambda plus mu power z minus x and then zx. This is just the mean of the binomial with this p, this lambda by lambda plus mu. This is x, summation is over x. So this will give me the n is z. The n here is z, right? This is n with z, and p is lambda by lambda plus 2. Is correct? No? This is what we get. This is what we get, this chi. Now, what is E of x plus y? Which is just chi of x plus y, right? So this is as a random variable. This is just x plus y, I mean as a constant times lambda by lambda plus mu. This constant times x plus y. But this random variable actually follows Poisson, constant times Poisson random variable. I mean, these two are, this is x is Poisson, y is Poisson, x plus y is also Poisson. Constant times a Poisson random variable. That's what we get as the conditional expectation. Even though the conditional density was binomial, the conditional expectation is again Poisson. To verify we are correct, you just take the expectation of this. E of x given x plus y, which is just, this is just Poisson lambda plus mu. So lambda into lambda plus mu by lambda plus mu, which is just equal to lambda, which is same as expectation of x. So we are correct. Okay. I mean, we just verified where we have done the computation correct. So any problem with this? Any question? Second last line here, here, before that E is, I'm writing it as E. This is the E, no? LHS is E of something, E with respect to that. That is what the summation is. The summation is E with respect to this conditional density. This chi of X, chi is just the expectation with respect to expectation of Y with respect to conditional density. Okay. And I mean, that's the definition, no? I have written there. Okay. This is here. Chi is summation Y, this. Okay. And that is what I have computed here. That is what I have computed here. And I got the binomial. Okay. That's what I got, I mean, when I do that, that's the mean of the binomial, which when you insert this X plus Y, you get again Poisson. By condition, you go to Poisson and something coming back. Okay. Something happening. So finally, you get something Poisson. And I mean, we haven't done any mistake by calculating the expectation. It is clear we haven't done any mistake. Okay, that's all. Okay, let me give another example where we combine binomial and Poisson. Okay, here two are Poisson and we this summation. This is the definition. From here to here. This is just the mean of binomial distribution. This is binomial, no? You have computed the mean of binomial. Mean of binomial is NP, where P is this and N is Z. Right? Mean of binomial is NP, N times P. Binomial is given by two parameters, N and P. Okay? N is the number of Bernoulli and it's independent Bernoulli. And so N times P. Okay, second example. Suppose we have x1, x2, or some xi. This is IID, independent, and each xi follows, what does it follow? Bernoulli with P. It takes value 1 with P, 0 with 1 minus P. Okay, Bernoulli random variable. Okay. Then N, which is a random variable, N independent of all these things. No, N is not independent. N is a random variable. I'm defining a random variable. Yeah. Some which will depend on this N. Okay. Whether I will need independence is not clear yet, but let me just write it. Okay. If I need it, I will just use it. Okay. N is Poisson with lambda. Okay. I have a sequence, countable sequence. Okay. I mean, xi, I in N. Okay. I have a countable family of independent Bernoulli random variables, and I have one single Poisson random variable. Then I define Sn. This is something in the assignment also, I think, one problem. So this is just x1 plus up to xn. Okay, summation x1 up to xn. Here the n is varying, as you can see. Okay, n is a random variable, which is so sum is a random variable which depends on this x and then n also. Exactly, that is the point. Okay, this is n. So the sum is the number of terms in this will vary depending upon each omega. See, if you insert a omega here, there will be omega inserted here. For each omega, there the n. I mean, see, there is a probability space in the background. Okay, for each omega, you have n omega. So you sum that many random variables for each omega. So you get a single Sn. Okay, if you want Sn of omega equal to x of omega of xn of, you can write it, but we don't do all that. Okay, we just define it like this because we don't need it. Okay, if we need it, we have to, I mean, invoke the n is integer valued random variable. Poisson random variable is an integer valued random variable. N is Poisson means it's integer random variable. Xi takes 0 or 1. This also takes integer value. This also integer value. Okay, when you submit, you get integer. Okay. Now we want to compute E of Sn given n. This thing. Okay. From using that, we want to compute E of Sn. Okay. Compute. And E of n given Sn. You want to compute these three things. Okay, this is the problem. So first E of Sn given n. This we want to compute. So to compute that, we have to first compute the conditional probability function. Okay, so f of Sn given n, and Sn I put k this time instead of x and y, k and n. Okay, I want to find the conditional density of Sn given n. So Sn equal to k, n equal to n. This is the conditional density I want to find. Okay. Okay. Poisson is independent. Okay. I need it here. N is independent of all those sides. Yeah. I mean, I need it here in the calculation here. Okay. X is independent. Okay. Now this is equal to f of Sn, the joint density Sn n k n divided by f of n n at n. The usual same formula which we have used few times. Okay, that is this. Now I'll just write all those things. Okay. Now it is given n equal to n, Sn equal to k. What is Sn equal to k? So x1 up to xn are binomials. Sorry, Bernoulli. When n equal to n, it is just binomial in n and this, right? Okay, this is in P, right? So this f of Sn n, this function, this is equal to this, and this is equal to this. So n equal to n is fixed. So it is just binomial, right? So this is just n of k, okay, then p power k 1 minus p power n minus k. That is for the Sn. Where I have written? Yeah, that is for the Sn1. You have to multiply with n also. I mean, this is the. Huh? No, Sn. Yeah, n is independent of xi. Yeah. So then it is just lambda power n by n factorial p power minus lambda. I'm using the independence. N is independent of all those xi's. N equal to n. I mean, if you want, you write one more step. Okay. It is just f of, this is equal to f of Sn n kn. Okay. Then you write this. Okay. This, right? This is okay. This is just Sn equal to k, n equal to n. Then Sn equal to k means n equal to n. So this is a Sn equal to this. Sorry, Sn equal to k. K, correct. When you assume n equal to n, this n becomes small n. That's what I'm saying. Okay. So that's what I have written. Then I take the product and write it like this. Okay. I mean, if you want, you write one step. If you want, you write this is equal to probability of that equal to this, then it will be more clear. Okay. You can write it if you want. Okay. So now I want to divide it by f n n. N equal to n. No, n equal to n. Yeah. Yeah. Wait a minute. Now n equal to. No, we are computing Sn by n. So that is just n. That is just Poisson, right? So I mean, Sn equal, that is just again lambda n power n factorial by 4 minus lambda, right? That's all. So you just, they get cancelled and you just get binomial. Nk p power k 1 minus p power n minus. Okay, this is okay. Right? Fn n, that is just, n is n is Poisson. I have written it again. So I cancelled it and we got it. This is okay. Okay. Now I want to compute E of Sn. I mean, if you want, you have to compute Sn by n. Okay. At wait, at k. At k, right? At sorry, wait. At Sn by n. This is a function of n. I'm also getting confused.
That we could have just treated as f of small n.
S of small n, yeah. Yeah.
And just that because we
Yeah, that get cancelled. Yeah, you're right. You're right. You're right. That's what I have written it more. Yeah, I mean, unnecessarily wrote it again. Yeah, you could have cancelled it earlier. You are saying. Yeah, correct. Yeah, you are right. He's saying that here itself you can write it as a product, and I mean, you can just cancel it with that. That also you can do. Okay, no problem. Yeah. Okay. So we have got. So now we have to compute this. This is just the conditional. I mean, expectation sum, which is just Sn given n. So you have to sum in this k, which is k n k p power k 1 minus p power n minus k. Okay. If you use this definition, chi definition. Okay, that is what we get. But that is just this is just Bernoulli, okay, in n. So it is just n times p. Okay, this implies E of Sn given n is just n times p. Now it's a random variable. Instead of n, you have to, this is just a function of n, where you have n here. Okay, then conditional expectation, you just have to insert the random variable there, where with respect to which you are quotienting. I have just inserted it, that is np. Yeah. Where linearity? Where? Yeah, but it depends on n, no? How will you, what is the linearity there? But we haven't proved linearity. I plan to give it as an assignment. Linearity of conditional expectation, we haven't proved yet. That I will give as an assignment. Okay. Yeah. But how will you do that? Because this Sn will, this number of terms will be changing, no? What is linearity? If x1 plus x2, you can take it out. This is x1 up to xn. How will you take it out? This x1 up to xn will depend on this n, no? How will you, where is linearity coming? There is no linearity. Yeah, but where is capital N equal to k coming? Unless you do this. Only here you are conditioning, you are fixing a value for n, capital N equal to n. As it is, you can't use linearity because this sum itself, number of terms in the sum itself is random. It is not fixed number of terms. Then you can use linearity. Okay. So this is the answer, NP. You try that, but by doing in the wrong way, we'll see whether you get the right answer. You may not get. Okay. Okay. Now we want to compute the expectation. Now it's clear how to compute the expectation. Now expectation of Sn we want to compute, which is same as expectation. See, now you can see that where that formula is useful. Yeah, expectation of Sn given n, which is same as this, and which is equal to expectation of n times p, which is just p times lambda. Easy. We know the expectation of n, which is lambda. So we got something involving p and lambda. Sn has expectation p times lambda. Okay, which is expected. Each variable has mean p, and the sum n has lambda as their expectation. So it should be p times lambda, which is expected, right? So that's what we get. I mean, we should get expected answer also in probability. Okay, now the final thing is we want to compute E of n given Sn. Okay. Okay, how are we going to compute? Okay, let me write it. So to compute it again, I have to compute this. We need this, of course, f of n given Sn at n and k. Okay, is this right? Yeah, this is what I was using, n and k. Okay, this is what we want to compute. Okay, this will be a big term, so I will just write it here. F of n given Sn, okay, and n k. Okay, this is what I want to compute. But this is equal to f of, tell me, n. Okay, let me just write it. This is just f of n Sn at nk divided by f of Sn at k. Okay. Of course, this is right. Huh? Just the usual formula. But this is equal to f of Sn n. Yeah, this is equal to f of Sn given n, which we know the answer. We don't know what is n given Sn. Okay, I mean even the joint also we don't know. We only know this. Okay, Sn given n. Okay, of Sn is k and that is n, and then we have to multiply by no, yeah, we have to multiply this divided by that will be there. No, so f of Fn of n divided by f Sn ft. I hope I have written it correct. Okay, if you find a mistake, you tell me. That's going to affect here. We didn't found. This is the other way we found. Huh? Yeah. This is just the joint density, no? Which one? That is f Sn given n. This one. This. Yeah. This is just the joint density, no? Yeah. That's we are going to insert, but.
I mean, fine. Yeah.
Here, that's what I have written.
Yeah. You want to change it.
No. There, see, there is a small problem there. There it is n equal to n. Yeah, it's the same thing. It's the same thing. Yeah. That's right. That is just binomial. Anyway, I'll just write it. Okay. Now this is equal to, first, this is, I mean, this is just by a binomial, right? Yeah. So this is just n k, okay, p power k, 1 minus p power n minus k. Then this is Poisson, lambda power n by n factorial, okay, e power minus lambda divided by, let me that right, huh? Yeah, we have, no, the n is there. What we fixed?
When we changed it, we fixed small n now, right?
Correct.
So now Sn is independent of capital N. So again, we can split it and cancel that out.
Yeah, when n is equal to n, Fn equal to k, we have computed. That's binomial. That I have written. Okay. Then this is this. Okay. Then now Fsn, that is Fsn at k. Yeah, this is just Fsn at k. See, this is just going to be f. So let me just write it here, and then I will write it on the top. See, this is equal to f Sn at k equal to, which is just probability of Sn equal to k, of course, which is just equal to, you will have a union, which I take it out, disjoint union, I take it out, summation m equal to k to infinity. Let me write it and then explain. Okay, probability of Sn equal to k given n equal to m. Right? Sn equal to is a random variable. N is random variable. Sn equal to k. Sn equal to k given n equal to n. Okay. This is just the disjoint n equal to m plus some other m prime. They are disjoint. So you can write it as disjoint union here. You can take it as a summation, which you have done. So I have written it as one step. Okay, this is clear. Okay. You have to write disjoint union here and then take it out. Okay. So this will become summation of m equal to k to infinity. Okay. This probability Sn equal to k given n equal to m. Okay. And this is just pi. This is again binomial, right? Because m has to be greater than k. That's the only choice. M is smaller than k. You don't have, I mean, from m item, how will you, when m is small, how will you get k items bigger than m? It's not possible. Okay. Right? It's not possible. It's just a sum, it has to be like that. So that is why. So m Ck, okay, p power k 1 minus p power m minus k times, then it is just lambda power m by m factorial times e power minus lambda. Okay, this is okay. This is okay. Okay, now I remove few things. There is a n factorial here, there is an n factorial here. I can remove. There is a k factorial here and there is a k factorial here. So you will get only 1 by n minus k factorial here. And here 1 minus mk factorial here. This p power k, this k is fixed, right? P power k and p power k we can remove. Okay, and here m minus k that will remain. There n minus k that will remain. This lambda n is there. Here we have e power minus lambda also I can remove. So I can remove this thing. So you have lambda power n and lambda power m here. Okay, but then yeah, this lambda power m is there. Yeah, let me write it. We will get something. Let me write the final answer. So what we have is the first term, we only have 1 by n minus k factor. Okay, fine. Then we have p power k is gone. Then 1 minus p power n minus k is there. And lambda. So we have m minus k there, right? So I take a lambda. Yeah, I write it like this: 1 minus p times lambda power n minus k. Okay? From the lambda, I take only n minus k there and leave the lambda power k, which I will cancel with the bottom one. So I will get a lambda m minus k there. Okay. Okay, lambda m minus k there. Other than that, the n factorial is gone. E power minus lambda is gone. Here this top m factorial is gone, and we have only summation 1 by m minus k factorial. Okay, and then we have 1 minus p power m minus k. Okay, and then lambda power m minus k. Right? That's what we have, lambda power m minus k. That's all we have, right? You have checked. You're looking at the computer and checking something. You're writing it? No. Okay. It is okay. 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 Now this is just summation from m equal to k to infinity. Okay. You can write it as m equal to 1 to infinity or L equal to 1 to infinity. M equal to, let me write it, m equal to k to infinity, which you can write it as L equal to 1 to infinity summation. Summation 1 minus p power m minus k by m minus k is, I got it, L power L factorial into lambda power L, which I can write it like that. And the top one I am not changing anything, L minus k factorial times, which is just 1 minus p lambda power n minus k. Okay, so the whole thing, I mean, if I call 1 minus p equal to q, okay, this is just q lambda power n minus k divided by e power minus lambda times e power minus lambda. This is okay? N starts from 0, you are right. I mean, then only we get e power lambda q. Yeah, n starts from 0. Then only we get that. Okay? Please check. You can do the computer. What happened to? 1 upon what? 1 minus n. Yeah, it's there. It's again, exactly. You will just write it. So we have just computed the conditional density. Now we have to take the expectation again, right? That's why you write it systematically, it will be clear to you. Okay. What I have done is the following. I just computed this, inserted all that, cancelled all this, and got this. Okay. That's all. Carefully done, which we 2-3 of you verified also. Okay. So that is this. I've got this. Okay. So this is the conditional density. Now you want to find the chi. Okay. What is the chi? chi of n given Sn, right? N given Sn at k. Okay, the k is the variable. So which is equal to, we have to insert where did I started from there, right? So f of n given Sn is k. Okay. No, I have to, sorry, I have to do the computation, right? Summation k, yeah, that is this k. This k, this is for all k less than or equal to n. Yeah, n, yeah, right? K less than or equal to n. So now I have to sum it over n. I'm sorry, I have to sum it over n. So which is just n equal to k to infinity. Again the same thing, n equal to k to infinity. So which is just q lambda power n minus k e power minus lambda q divided by n minus k factorial. Okay. Where n? Where n? Yeah, there is a n here. That's what there is a n here. That's what you said. Which is equal to summation, you change it to m equal to 0 to infinity, m plus k, right? I'm calling n minus k as m. Okay, m plus k of q lambda power m by m factorial e power minus lambda q. This is just the, if you have m here, it's mean of that. The other one is, no, other one is just k is a constant. You can take k out, which is just the, which sums to 1. Okay. So this is just m times the lambda is q lambda, okay, minus, minus lambda q, right? Plus k. Finally, the answer is so simple. Is fine? Okay. Now what we get? Now we got f of n given Sn. We want to find. We just have to insert k. No, not minus lambda q. Just lambda q. Sorry, that is a mean. Mean is just lambda q. Okay. So which is just lambda q plus k. K is the random variable. So this is the answer we have got. Yeah, by a constant. Okay. It's just n given Sn is this. To verify we are correct, we just compute the expectation. Okay. Now we compute E of n given Sn, the expectation of this. That is going to be lambda q is just lambda q plus q, k, not k, this is n, sorry, this is Sn, I'm sorry. There is no k, sorry. Since I had a small k, I wrote big K, sorry. This is Sn. Okay. This is Sn. No, this is n Sn, right? Sn. Yeah, Sn. Correct. Sn. Yeah. If you stand here, you will get more confusion. Okay? If you write it on a paper, it will be easy. Okay. This is Sn. So now if you compute this is just constant Sn. Now, which is just p lambda. We have got lambda q plus lambda p is just lambda. 1 minus p. This is 1 minus p, which is just lambda. So which is same as E of n. So we are right. This is one way of verifying we have done correctly. Okay? I mean, this need not be correct, but I mean, this need not verify that everything is correct. Just to make sure we haven't done any mistake. Okay, we have completed. Oh, that clock is not working. Yeah, I have time, more time. Okay. Okay. So these are two examples. Now I want to give the algebraic meaning, what it means by a conditional expectation. Okay, we'll do it there. Okay, before that, so this is the proposition. There are two parts. One is we have proved this E of y given x If you take the expectation, you get E of y again. Okay, we have proved it. We proved the generalized version of this, which is the same proof. E of g of x, you take any function of x times y. Oh, 1 second, wait. Yeah. E of g of x times E of y given x. This is equal to E of g of x times. Okay. Okay. 2. E of if E of some g of x, if suppose chi of x, g of x. Okay. So let chi be chi and phi be two functions. Okay. You have two functions. Yeah, this is if you want phi1, phi2. Okay. I mean, this is related to chi, but this is related to chi. Chi is one such function, but I am saying that the chi is unique. It satisfies this condition. So to say that I am saying phi1, phi2, you take phi1, phi2. Chi is one, phi1, phi2, chi is one among them, and it is unique. That's what I want to say. If this is equal to phi1 of x, okay, equal to E of phi2 of x, g of x. If for all g, since we are working with discrete random variable, we use any function. Okay, there is no condition on the function. Otherwise, we need some condition on the function. I mean, we cannot use all type of function when we use continuous random variable. Since it is discrete, we are freely using all function. Okay, any function is continuous. For example, discrete random variable. Okay, every function is continuous. Okay, so for all g, then P1 is equal to P2 almost surely. That is probability of P1 x equal to P2 x equal to 1. Okay. This is easy. That is also easy. That is just the same computation as the earlier computation. I should leave it as exercise, but since I am giving some other assignment, I will do this. I am giving some assignment. So, or shall I give this as an assignment? No. We will as assignment. It's the same, this as assignment. Okay. Same proof as except we have g of y. Okay, I will write it. Okay, this is what is that. You want to compute expectation of this. You just do this. You want to compute expectation of this. This is a function of x. Okay, chi of x. This is a function of x. Okay. So if you have two function of x, it is just that is going to appear here, which is the summation. This expectation is summation x in R, summation over x, g of x, and then we have a chi of y given x, right? Of x. Okay. Then fx at x. Okay, this is the expectation, right? This is the E of g of x, E of y given x. Okay, which is equal to this. Okay. Okay. By definition of conditional expectation and all that. By definition of conditional expectation, E of any function h of x is just you take small x and x, and then this is the definition of conditional expectation, right? I'm just using that. I'm just using the definition. Here you have two functions, E of x times. This is a function of x. So that's why I'm using it. Okay. Okay. Now we have to write what it is. Now summation x and g of x. And this is summation y. This is summation y. Okay. Now you can take, there is no y here. You can take that also here. Or you keep it here. It will get cancelled. Okay. No, it may not get cancelled. Okay, let it be here. Fxx. I think it will just joint. We will get the joint one, I think. Whatever. Yeah, it will get cancelled, right? Yeah, it will be here. So then this we have to compute. This is just y times f y given x we have to write, which is just f xy by fx at x, right? Right. So you cancel these two things and you get only this. And this is equal to summation x, summation y You write everything. So summation x, summation y g of x times f x y xy. We have computed the, if you have a function from Rn to R, if you have a function, we know how to compute the random thing. No? That's the first thing we proved. If you have a function from chi, this is a different chi, maybe phi from Rn to R, okay, then you want to then phi of x1 up to xn, if you want to compute, which is just summation of, you have, then you multiply by the joint density and do that. Okay, we have used that formula, we have proved that formula. If you use that formula, we get this. I mean, this is equal to expectation of y x. If you use that formula, we get this. If you have a function from Rn to R, okay, and x1 up to xn are random variables, p of x1 up to xn. If you want to compute the expectation of this, this is just p of x1 up to xn, summed over x1 up to xn, summed over Rn. Then you write the joint density here. Okay, that I'm using for these two functions, y times gx. Okay, then we get this. Y times g is the function of two variables. Okay, that is what I have written. So I got the answer. So first one is proved. Okay, let's prove the second one. Oh no, it didn't change this. Anyway, it's an easy verification. One can just directly write it. Okay. Okay. Now the second one, let me write it here again. Suppose e of v1x g of x equal to, this is just nothing about conditional expectation. This is just about expectation, about g of x. This is for all g. So phi1, phi2 are given, two functions, such that this happens. Okay. Then we want to show phi1 equal to phi2. Everything is continuous here. We are discrete where everything is continuous. Okay. So everything, whatever the property you use, there is no differentiability. So if you want to use, so this is just phi1 minus phi2, okay, times x times g of x equals 0 for all g. Okay, take g equal to, if it is complex number, you have to take bar, but since we are working with only real, you just take phi1 minus phi2. This implies e of phi1 minus phi2 square of x equals 0, right? Or phi1 x minus phi2 x square equals 0. Okay, e of x square equal to 0 means x is a constant random variable, right? You know that, no? You have seen. So this implies phi1 minus phi2 equal to constant, which is just the mean of that random variable. Okay, constant random variable, almost surely with probability 1. I mean, sorry, p1 x. I mean, it's a statement on random variable, not on the function. Sorry. I mean, there is no phi1 minus phi2, there is no probability. They are defined on real line, there's no probability. On the probability space, it is true. This line to this line, this line to there. You take phi1 minus phi2, this is same function you take, I'm saying. Same function take you, then it's just square, no? This is phi1x minus phi2x. I mean, to notice that I have written it like that. This is just p1x minus p2x, which is same as p1 minus p2 or times x, right? So p1 minus, this is just a way of writing. Okay, this is p1x minus p2x. So you take g is equal to p1 minus p2, so that you get the square of that, which is just p1x minus p2 square. Okay, so that is equal to 0 means p1x. So this implies p of p1x equal to p2x equals 1. That's all. Okay. So what does this say? I move it up. This is just the proof. Okay. What does this say? So first, this function satisfies this. Okay. You can use this definition of conditional expectation. Okay. E of y given x is the unique function of x. Okay, unique, if you wish. I mean, chi is just chi of x. I mean, a function of x, unique chi of x. Okay, such that e of chi of x y is equal to e of chi of x, sorry, g of x equal to e of y times g of x. See, you have x, one random variable. E of y given x, okay, which we defined through something, is the unique function. So there exists a function chi such that this is satisfied. I'm just saying E of chi of x is the unique function of x. Unique, if you want, you write it as unique function of x. Say that is chi of x. Okay. This statement is okay. There is no problem. I'm saying E of y given x is a unique function of random variable x, say which is chi of x, such that E of chi of x g of x equal to E of y g of x for all g. You can define this as the definition of conditional expectation, provided you exhibit existence. We have proved the uniqueness. I mean, when you want to define a function, first it has to exist. Second, it has to be well defined. Well definedness. I mean, the well definedness is this, right? If there are two options, then they are same. Almost. I mean, we only worry about almost sure. Okay, with probability 1. So they are same. The existence we have proved already. If we can prove the existence through some other method, then that is enough. Some other method. For example, this is one method. I'll show you one method. This is not for all functions. Suppose if you have a finite probability space, okay, then this works. If it is not finite probability space, then you can do the following. Suppose L2 is all square integrable random variable. Okay, square integrable random variable. That is E of x square is finite. I mean square. Okay. Sorry, I'm with the measure theory. I'm just stuck with that. All with second moment, with finite second moment. All random variable with finite second moment. Okay. This is okay. This makes sense. That's what I said. So square integrable. Okay. Okay. This is okay. Now you have a y in this L2. Okay. I mean, you don't need to understand. This is not part of it. Just I'm telling you this. Okay. Now y is in L2 and x is also in L2. Okay. So you take a subspace. How would we do it? V equal to all those phi of x such that phi of x is also in L2. Okay. Okay. Now this is a vector space. This is a vector subspace of this. Right? And this is an inner product space. This is an inner product space. This is an inner product space. Okay. Yeah. Now this, if you have a y here, okay, y is taken, you take this E of x, I mean this is just composed of phi of x, all those things. Now phi of x going to E of y phi of x. This is a number. It's a linear functional. Okay. Do you know any linear functional, how it is given on a, for example, in a finite dimensional vector space? Any linear functional? It is given by inner product. It's given by an inner product. It's not true when it is infinite dimension, but when it has an inner product, it is true under some condition, closeness and all. There are something. You don't worry about it now. So this will be actually equal to E of some chi of x times P of x. That chi of x is exactly the conditional expectation. Makes sense? So that is why we don't need to go through all the calculation. This is just can be defined algebraically. Which definition? This definition. This definition says the following. This is a different definition. E of y of x is the unique function chi of any function of x. It should be a function of x cannot give all random variable, right? Suppose x has range is only 2 points. Then if you take chi of that, that will be less than 2 points, right? The range will be less than 2 points. So you cannot, obviously you cannot have all the range, for example. Okay. So chi of x is something does not give all the random variables. Okay. So E of y of x is a function of x, which is the unique function chi such that it satisfies this condition. When it satisfies this condition, this has to be there cannot be two things which satisfy this condition, because then by that second one, if we have two functions phi1 and phi2, phi1 should be equal to phi2, or chi1 chi2, or chi1 equal to chi2, right? Okay, because of that the function is unique, so it's well defined. Existence we proved using something, we proved rigorously through something, or I am saying you can do it through this. This is not part of our syllabus. I am just telling you, informing you. Okay? So you can use this inner product. This is what is called Riesz lemma, and using that you can do this. Riesz lemma is if any linear functional on a closed inner product space. It should be closed, which is called a Hilbert space. If you take the inner product will give you a norm, and the norm will give you a metric. And using that metric, you can have a complete. You have to have a complete space. On that complete space, any linear functional will be given by an inner product. I mean, it will be a dot inner product if the dot will be here. Whether you are a mathematician or physicist, you know, physicists use inner product with the other way. First, for us, I mean, you are a physicist. Okay, for us means for me. First one is linear, second one is conjugate linear. That is the usual. But here everything is real, so you don't have to worry. Okay? Yeah, this is just there. This is, I mean, there is no complex. Complete norm. Yeah. Yeah. With inner product, it is called Hilbert space. Okay? So if you have Hilbert space, L2 is a Hilbert space. Subspace is also a Hilbert space. It is closed. Then you can you can define the conditional expectation using this Riesz lemma. This gives a linear functional that is actually given by that, and blah blah blah. If you want, we can discuss later. Okay, that is done. Okay, so this is the property. Now I want to give the assignment. Okay, assignment which you submit with the same assignment. You want more time, no? It's just it will few statements will take the time to write the statements. That's all. Okay, it's very easy to verify, like linearity and other things. So there is only one thing which you need to verify. You need to do the calculation, which is same as this calculation what we have done. Okay, I will orally tell you the proof also. Okay, so assignment. Let me see how much time I have. 10 minutes I have. Okay, the first one is E of ay plus z given x is same as a times E of y plus E of y given x plus E of z. I mean, you should submit before midterm. It's better, because exam you will have more complicated questions, and then you write this. It doesn't make sense. So it's better you write these things before midterm. That's what makes sense. Okay, if you write it after midterm, unless you do the exam very badly and you want to submit the assignment for some mark, then it makes sense. Okay. It's better to do it before midterm, okay? Because you will get more, more not complicated, more involved questions than this in the exam, right? So you better do it before that. This is easy, but direct verification, you can just do that. Okay. And then is if y is something greater than 0, then E of y given x is also greater than 0. That is also clear. But this is an important property. Okay, this is called positivity preserving property of the conditional expectation. Okay, then this I will tell you the proof. These two are easy, direct verification. E of g of x y given z. This is what is called x. This is what is called linearity, extended linearity, generalized linearity. You can take any function of x outside the conditional expectation. You just write the definition. Okay, you just want to compute this conditional expectation, which will be this is y g of x you have got. Okay, which is now you want to, I mean, you just write the definition of it. G of x, y, I mean, the density function and all that. Then you will get, you can take out the g of x out. Okay? You write it clearly, what is equal to what, then it will be clear. Okay, you just take it out, it will be there. Okay, it is the fourth one slightly involved. Okay, these two are just trivial. You will take the time to write it. That's what you don't need to think. Okay? You have a function g of x, y. You take the expectation with respect to x. You can take the g of x out. You can, if you want, I write it like that. Is this what is called? Okay. Then there is no confusion. No? You can take the, this is like linearity with respect to, or if you want, if you know something, it's like a module property. Yeah. Keep your capital X, right? Capital X. Capital X. Does it look like small x? No. Capital X. Okay. Then the next one is E of, this is E of y given, see this I haven't defined, but you can define the same way. You can take two random variables, x and z, and define this. Please write the definition. Okay? It's the same thing, except you f of y given z and x and z. No, x equal to x, small x, z equal to small z. You just write it. Yeah, you just exactly. You just write it, write the definition. You will, instead of the bottom, you will get the joint density or whatever. You write the correct definition of it. Okay? That you take it. So this gives a random variable. Now this will be a function of x and z. Right? It will be a function of x and z, as you can expect. Now you take it with respect to x. So you get y z. Z has no role to play. Of course, in the expectation, z has no role to play. It's something similar to that. Right? When you take expectation of E of y given x, you just get E of y. X has no role. What is in the bottom has no role, right? When you take expectation. You quotient with any random variable, take the expectation, you will get the original expectation, right? The x has no role. Similarly, if you have y thing and then take the x, the z has no role. Sorry, x has role. Sorry, x has role. Sorry, I'm sorry. This is not z. Expectation with respect to x, you get x. No. This will be a function of x, no? Exactly. That is what I was saying. If you take expectation of y given x and you take the expectation, you get E of y itself, right? You forget about the x. So similarly, this is just the extended version of that. Okay, you take with respect to x, you get this. Okay, which is also same as this is very easy. This follows from the earlier one. This one, E of y given x, which is a function of x. So then you take x and z, then you should get the same thing, right? Which is already a function of x, which is a function of x and z also. So if you, so in particular, this says if you take, if there is no y here, if you have a function of x, E of g of x is just g of x. Yeah, okay. If I forgot one more thing, maybe 3-2, E of any constant c given any x is just c itself. Okay. And another one, sorry. This is 4, this is 5. And this is direct. C given x is c. That's clear. Okay. So it is like if you have a g of x, you will get g of x out. I mean, if you take y equal to 1, E of g of x is g of x. Okay. I mean, E of g of x is g of x. I think I have said whatever I want to say about conditional expectation. Okay. Yeah, we'll stop.